This is part 1 of section 6.5, graphs of polar equations. So what we did in our last section, 6.4, is talked about the relationship between rectangular and polar coordinates, how we go back between the two, how we define polar coordinates. What we're going to do in this section is talk about graphs of functions, and these are functions that can't easily be described with rectangular coordinates. If we do describe them, they have to be done in 2 or 3 equations. Now, the thing about polar equations is they are functions even though they violate the vertical line law. The reason for that is that it doesn't apply. It's only defined for the rectangular system, and each theta you input gives one output, so it meets the definition of a function. So let's start with what it means to be symmetrical in the polar system. So there's 3 basic types of symmetry that we use, and the first one is with respect to the polar axis, or what we commonly know as the x-axis. So how this works is that we're going to test for symmetry. You're going to replace theta with negative theta. And you want to see if r of theta equals r of negative theta. That's what you're looking for. You also can try, depending on the complication of the equation, you can always replace theta with pi minus theta. So then you're looking for negative r of theta equals r of pi minus theta. So in the picture, what you have is, let me make this a little bigger. You have a situation where from the polar axis, the horizontal axis, you have a point that's at like 2 pi over 3 right there, so that's plotted like that. And you have another point plotted at negative pi over 3, 2. You can see that they are split across the polar axis, that they are symmetrical. So that's our first type of symmetry. Our next type is symmetry with respect to the line theta equals pi over 2. Now that, of course, is the y-axis. So what that looks like, to test for it, you replace theta by pi minus theta, because what that does is it moves us 180 degrees, or to the other side of the line pi over 2. The other way you can do this is you look at negative r and r of negative theta. Again, because we're dealing with a circular coordinate system, that's why you get this idea of more than one way to find the symmetry. So when you look at the picture, so we're talking with respect to the line pi over 2, which is the y-axis. So we're at 3 pi over 6, which is here. So it's that point. Oops. Not very straight. There we go. And the other point would be 3 negative pi over 6. Or, if you think about it, this is a perfect example why the other one works. That's 5 pi over 6. If you take pi minus pi over 6, you will get 5 pi over 6. So there's where the other point is. And you can see that they are symmetrical over the line pi over 2. So that's our second type of symmetry. Okay, and our final type of symmetry is symmetry with respect to the pole, which we also know as the origin. And so what we want to do is we have two ideas here. We can replace r with negative r, or, so we're looking for r of theta equals negative r of theta, or we're looking for r of theta to equal r of pi plus theta. Because this is like odd symmetry in the rectangular coordinates. So if you have a point here, if you have a point there, the symmetry with respect to the pole will be here. So there's two ways to look at that. You can think of it as plotting r theta and then making theta negative, which would take you around here, or you can think of plotting this point and then saying what is negative r, and so that point would be there on the opposite side. So either way, you are opposite the pole, and that's what you're looking for. Okay, so what do we do with these? One thing to keep in mind that these tests are sufficient to say you have symmetry, but they're not necessary. So what that means is you're going to see some graphs that have other types of symmetry, or they might have this type of symmetry, one of them, and they might be symmetrical with respect to the line pi over 3, or some other part of the graph. So that's what that means. So we are going to look at some special types of graphs. There are families of graphs that have special names, so we're going to investigate them and then talk about the properties of each one of these families. So the first one we are going to do is the graph r equals 1 plus 1 sine theta. So the best way to start these is by testing for symmetry. So that's the first thing we're going to do. We're going to start by check for symmetry. So we're going to go through our three types of symmetry, and that'll help us determine what points to choose to draw this. So the first thing we're going to do is the polar axis. When we look at the polar axis, we're going to substitute negative theta in. So r is going to be 1 plus 1 sine negative theta. And since sine is a odd function, this will be 1 minus sine theta. So that is not the exact same equation, so it does not have polar symmetry. The next one we're going to try is theta equals pi over 2 symmetry. And when we do that, we're going to do r equals 1 plus sine theta minus, pi minus theta. And now what we're going to do, and you can see why we learned certain things in this class, we're going to use our difference identity and write this as sine, should put a big plus here, sine pi cosine theta minus cosine pi sine theta. And when I do that, I'm going to have 1 plus, now this part is going to go to 0. Cosine of pi is negative 1, so I end up with a plus sign there. So I have 1 plus sine theta. So I get back what I started with. So this is a yes. And then finally, we have symmetry with respect to the pole. When I do that, I want to see, is negative r equal to 1 plus sine theta? And you can also check these by, if it doesn't work one way, I'll show you, you can check the other one. And we'll see that in a couple of the other problems. So if I distribute that negative, that is definitely not the same. So this is also a no. But what I'm saying is you could try doing this, you could try a different symmetry. So then you could see if r equals 1 plus sine of pi plus theta to see if you get the same thing back. And you're not. You're going to get this equation back because you'll have the situation here, but you'll have a plus sign there, so it'll make it r equals 1 minus sine theta. Go through and do that if you need to be convinced of that it doesn't work for that one. Okay, so now we know we only have to graph, since we have symmetry with respect to pi over 2, we only have to graph points between, I'll mark this up, then I'll take it off, right here, and then we can just reflect them to this side. So that's what we're going to do. So it's less points we have to graph. So let's set up our table. So here's theta, here's r, and so I'm going to pick negative pi over 2, negative pi over 3, negative pi over 6, 0, pi over 6, pi over 3, and then pi over 2. So you can see I'm going to start here, and I'm going to work my way up to there. That's my goal. Okay. All right, so substituting, we get a negative pi over 2. Let me just write our equation under the grid again so we have it to refer to. So r equals 1 plus 1 sine theta, or just sine theta. So we have negative pi over 2, that's negative 1, so we have 1 minus 1, which is 0. And then negative pi over 3, so we're going to have 1 minus the square root of 3 over 2, which is about 0.13. And then that's negative. Forgot the negative. And then negative pi over 6, this is 1 minus 1/2. So this is a half. Here's where your unit circle is going to come in handy. 0, you have 1 plus 0, which is 1. Pi over 6 is going to be 1 plus 1/2, so that's 1.5. And then we have 1 plus square root of 3 over 2, which is 1.87. And then pi over 2 will be 1 plus 1, which is 2. Okay, so go through those points in more detail if you need to see. Use your calculator where I got all those numbers. So what we're going to do is we're going to start at negative pi over 2, and we're going to plot the points, and then we're going to trace them in that order. So at negative pi over 2, I'm at 0. At negative pi over 3, I'm at negative 0.13, so I'm like right there. And then at negative pi over 6, I'm like at a half. And then at 0, I'm at 1. And then at pi over 6, I'm at 1.5. Pi over 3 at 1.87. And finally, at pi over 2, I'm at 2. So I am going to trace these points in the order that I did them, and then I'm going to reflect them. So I have one here, I have one here, I have one here, and then 1.5, 1.87, and then 2. So those are my reflected points. So this shape is called, looks kind of like a heart. It is called a cardioid. And the maximum length of R is going to be 2 units. Okay, I'm going to stop there for the first video and pick up our graphing in the second video.